So I'll briefly discuss with you an alternative way to compute the potential function. Okay, we already looked at one standard way. There's another, okay? And physicists like to use this other way in general, okay? And what you do is you take advantage of the fundamental theorem of vector line integrals. Now that we know it, we could do so. You can start A at some point which you call a reference, okay? So you just set A to some point that you call a reference. And this could be anywhere, generally it's chosen somewhere convenient. And you let B be arbitrary, okay? But for the purposes of integration, to get phi, you think about this as fixed, even though after you do the integration, you really consider it arbitrary, okay? And the fundamental theorem of vector line integrals tells us this: for any curve C that begins at the reference and ends at the arbitrary point R. And you could now write phi r and get it in terms of phi at this reference point plus a line integral, okay? So let's take a look at a quick example. We've already computed the phi of this conservative vector field here. Now we're going to do it. We're going to choose a reference point. We're going to do it in this alternative way. We're going to choose a reference point at the origin for simplicity's sake. It could be anywhere, and you'll see why you have that flexibility in a second. And we're going to choose C to be a straight line from the origin to an arbitrary point xy. So what's your first step when you want to directly compute a line integral? You parameterize the curve. Here's a simple parameterization that begins at 0 and ends there. It's a straight line. Okay, no need to complicate this. We're going to just take we could have taken a curve, but a wild curve, and the fundamental theorem of vector calculus will demonstrate to us that we're going to end up with the same answer due to path independence. But we're going to choose the simplest cases, and that's how you always do these. So writing this out, you'll have phi xy is equal to phi 0, 0 plus, and now you take your vector field with the parameterization plugged in. This is the parameterization. This here is x of t, that's y of t. Okay, so these are all, that's where these t's are coming from. Okay, and you then have, once you take that dot product, and we're integrating over dt here, okay? We're treating x and y as fixed during this integration, even though they're arbitrary after we finish. So you do the integration, and I won't go through the details here of this one. You just use integration by parts using that. Okay, but if you do that, you'll end up with this result right here, which could be written as ex cosine y plus some constant. Well, that's exactly what we found, okay, earlier. You could just absorb phi 0, 0 minus 1 and just call it a constant, because that's what they are. And so we end up with phi exactly as we wanted it to. There goes an alternative way to compute the potentials. There's even yet another way, but that one is a little more complicated, where you would use some actual formula integral where you use Green's functions. But we're going to avoid things like that.